Hello, I am Cam Gerlach, and this is an introduction to Project Mjolnir, a modular open source platform for developing scientific Internet of Things sensor networks. First off, I'd like to thank my collaborators and the other people who made this project possible, most especially Dr. Bitzer and the entire UAH HAMA group, Dr. Nair and the ATS 590 participants, David Corridor, Ryan Driver, and the NASA NSCCC engineering and IT teams, and the members of the Spider IDE team. So I'm sure everyone by now has heard of Internet of Things, but only now are we really starting to see their advances applied to the scientific field due to a convergence of factors, a variety of low-cost sensors to record scientific data, 4G in order to connect them, cheap single-board computers to run the whole system, like the Raspberry Pi, and a number of cloud servers and middleware providers to handle all the data, plus lots of buzzwords, which means, if nothing else, it's a popular field. But wait a minute, something's missing. Well, we'll get to that in a second. Let's start at the beginning. So, our idea was we have this array of lightning sensors that map 40 lightning locations. What if we use a Raspberry Pi connected to the system in order to collect a bunch of data on how the sensor is performing so we can see in real time if we need to do something about it? Well, so as these things go, requirements start creeping in. First, we had to get data from the solar controller. Then we had to get sensor status packets from the sensor. Then we had diagnostics telemetry from the Pi. Add to that ingesting and writing the actual raw sensor data, 22 megabytes a second. And then now remote control of the power system and the sensor. And add to that, now we're going to have to add real-time lighting data. Well, things are getting kind of complicated, aren't they? And wait, there's more. There's also the server-side component. Well, we got to receive and store the data, generate a website with an interactive dashboard with data. We got to issue alerts when something's wrong so we can do something about it. We have to send control commands and configuration to the Pis to actually tell them to do things. And then there's the good old real-time lightning data processing component. Again, complexity increasing rapidly with time. And you can see the hardware, it started out pretty simple and got more complicated. We changed some things around and slowly things got more proven. So the hardware's looking good. Well, the software, it looks quite complicated already. Now it just gets more complicated. We start to complete some things, but it's still a highly complicated system for a research group to manage. And so as requirements kept growing and more of the problem tended to be common infrastructure as opposed to just the actual data itself, we started to find that other research groups were having the same problem. Not only our HAMA 2 lightning sensor network, but also the eMesh statewide grid of high-density, low-cost sensors, various experimental sensors that groups use for uses, as well as UAV and aircraft deployed platforms, as well as more on the horizon. And we found that we were all looking for some sort of shared IoT client framework because we have tons of middleware and cloud platforms, but we don't really have any client platforms that actually can run on a Raspberry Pi and can ingest a variety of data types and output them to a variety of formats and do a variety of things in between. There just isn't those flexible open source frameworks out there. There's lots of proprietary data loggers, and there are some open source options, but they're mainly tuned to very specific sensors. There's lots of sensor interface libraries, but there's no common way of actually using each one in some core framework. And so it takes a lot of time, effort, and programming knowledge to actually build a data logger for any specific bespoke purpose. And every time you have to record some different sensors or different data, you got to write that all over again. So there's a ton of potential out there with all the factors in play, but there's a significant barrier to doing novel quality science with all these cool sensors. So enter Mjolnir, a flexible, easy-to-use open-source Python framework designed for low-cost scientific sensor networks with a robust client, an experimental server, a dynamic data dashboard, a lightweight plugin system, declarative device presets, and a centralized configuration. As the variety of common infrastructure that any IoT client system needs, particularly one working with scientific sensors, as we discussed before, as automated install and deployment for easily setting up your system, as of course periodic as well as on-demand data ingest, as recording and uplink functionality, as a multi-threaded real-time processing system so you can handle multiple threads of data at one time. You have status and error logging, robust error handling, configuration management, installing and running as a service, and of course, dynamic data visualization component, all under one roof. As you might expect, Brokkr, the client, has out-of-the-box support for a variety of input and output formats that a scientific sensor network may need, such as SPI, I2C, SMBus, GPIO, analog, UART, Modbus, TCP, UDP, and OneWire on the input side, covering basically all of the available protocols for reading in sensor data. And on the output, it has print, binary file formats, CSV, outputting to syslog, and HTTP formats currently implemented, as well as TCP, REST, UART, and wireless outputs under development. Even at this early stage, due to the ease at which new presets can be created, Brokkr supports a wide variety of devices right out of the box. These include various diagnostics, temperature, humidity, and pressure sensors, ADC boards, soil moisture, various industrial control devices, GPIO, anemometers, and more. Meanwhile, on the server side, the Mjolnir framework offers data ingest and processing, as well as a real-time interactive data dashboard. Its backend is fully static, with all the interactivity being done on the front end, so you can actually deploy it right on your IoT devices, as well as on free hosting providers like GitHub Pages or other static web servers. This allows remote and local monitoring of your sensors, downloading the data, building APIs, running diagnostics, and more. Let's go over some key concepts important to understanding how Mjolnir works. A unit is what we call one client as part of a larger system, and a system is what we call a group of sensors working together to achieve a common purpose with a common configuration. There are three key classes important to understanding Mjolnir's core processing. A pipeline step is one atomic unit of input, processing, or output performed as part of a series of steps. A multi-step is a set of pipeline steps, either executed in series or in parallel. And a pipeline is a set of steps and or multi-steps executed in sequence, with the output of one feeding the input of the next. Let's look at the four main types of pipeline steps. An input step typically takes in data from an external source, like a sensor, IPC or device, and being at the beginning of the pipeline, outputs it to the next step. An output step is typically near the end of a pipeline and takes in data from the pipeline and outputs it somewhere external, like a file, API, or network link. A transform step takes in data from a previous step, does something to it, and outputs it for further steps. And a unit step typically doesn't take in any data or output data and is self-contained, running in its own pipeline. Most of what you do with Mjolnir will likely concern what we call a system configuration package, where all the system-specific configuration for your system lives. There are three main components: your main config file, which defines the pipeline's presets and settings to use; the presets, which are the device-specific declarative configuration for a pipeline step or a plugin; and your plugins, which are just pipeline steps but implemented in an external file or a package instead of as part of the Brokkr core. Mjolnir uses .toml for its human-facing config, which is much like INI that you're familiar with, but just more powerful and easier to use. Your system config package centralizes the setup for your entire system with all its units, but any parameters still can be overridden in your local configuration. The configuration can be remotely managed and updated via Git, allowing all your clients to pull down new settings, but also allowing you to track any changes that were made. As you might expect, your system config package contains your configuration files, plugins, presets, and some metadata. Finally, let's go over a quick overview of the primary subprojects that are part of the Mjolnir framework. Brokkr is the client, run on each unit device. Sindri is the server that generates the dashboard. Mjolnir config template is an example system configuration package that contains numerous template presets and plugins for you to get started with. Mjolnir presets is the community-maintained repository that contains presets for numerous sensors and devices. Mjolnir website is the GitHub Pages repo that shows the live demo site. And Mjolnir HAMA and Mjolnir ATS 590 are system config packages for two operational systems. So now we're going to take a look at the Mjolnir client, Brokkr. To get help on Brokkr, you just type Brokkr-H, and you can see all the commands that are available. If you want to get help on a particular command, we can type Brokkr, say configure system-H, and we get all the options and settings for that particular command. So as we see here, if we just want to see what systems we have registered with Brokkr, we can just type Brokkr configure system with no arguments, and it prints a list of the systems registered. We can see we have several there, and ATS 590 is the default. If we want to specify a system explicitly for any Brokkr command, we just type Brokkr-s system, in this case, system Schema, and then to actually get a snapshot of what the current system's monitoring pipeline sees, we can type Brokkr status. And that gets us a look at the current output of the monitoring pipeline for that system. We can see the names are printed in human readable format. We have units and we have tolerances. Other things can be displayed there too. So, but if we want the data to be continuously updated, we type Brokkr monitor. This is for the default system, and we see we have our sensor data there continuously updated as fast as Brokkr can get it every second or so. Again, everything's pretty printed with units and values. So these options are intended for quick interactive use to quickly see what the sensor is doing or see if your system's working. For production use, you would use Brokkr start, although you would use it as part of a systemd service unit that we had built right in the background. But here I'm just going to run it in the foreground just for an example purpose. You see it output some log output. And then it's logging the data right now as we wait. And if we stop at Control-C, and then we type less to browse our files here, we look at the monitoring, we type the name of the current CSV. We can see there, that's our output data that we just logged with Brokkr. So that's an introduction to the Mjolnir client, Brokkr. Now, we are going to show you the data dashboard of Sindri, the server side of the Mjolnir framework. We can see here that we have the dashboard of all the key parameters for your sensor. Again, what shows here and how it's shown is fully customizable. We have the value. We have a gauge showing the current and 24-hour max and min values. And we have the delta, the change over time, all color-coded via a global color table that you set up that can highlight potential values of interest. If we keep scrolling, we can see the plot of the most important channels of data over 30 days. But we can actually zoom it in because this is a fully interactive plot via Plotly, and it shows you the values for the particular period of interest, as well as a little pop-up that shows you the current value of the unit, the name, and the time at which it was recorded. You can zoom right back out there and keep scrolling. We can see this is the raw data that Brokkr records, and Sindri just displays it all automatically, the current value and the 24-hour min, max, and average. Again, all color-coded to identify values of interest. If we keep scrolling here, we can see the data archive. This shows the values for with various summary statistics that you set up for each day. And again, highlights values of interest. And if you click on the day, it will show you the full version of the data, including a data table and a plot for that day. Finally, we have the log here of all the important events that Sindri sees, including most particularly errors and warnings in the system, and those will be highlighted for your attention. You can view the full log by clicking here. Finally, if we scroll back up, we can notice if we make the window smaller, the content dynamically reflows to fit the size, because it's a fully responsive layout. If we make it even smaller, let's say to the size of a phone, it goes to a single column layout, and we even have a hamburger menu here to easily navigate the page on a mobile device, so you can keep track of your sensors on the go. So that's the data dashboard of Sindri, the server component of the Mjolnir framework. So here's the big question. How can you use Mjolnir for your project? Well, first of all, we support single board computers running Linux, such as the popular Raspberry Pi for production, and Windows, Mac OS, and Unix and Linux for development. You can work directly on the single board computer, or you can develop and test your system config package locally on your own machine and then deploy via Git, GitHub, or GitLab to your production devices. It's easy to get started with Mjolnir, especially if you have a system config package already set up. First, you want to create and activate a virtual environment or Con environment, then install Brokkr in it with pip install Brokkr. Then you want to clone the Git repo for your system config package. Here we use Mjolnir config template. You can register the system with Brokkr by entering a name for it and the path. You initialize the local configuration with Brokkr config in it. And finally, you can run Brokkr status, Brokkr monitor, or Brokkr start to see output from your sensors. Let's say you wanted to create your own system configuration package. Well, that's easy too. First, you can just copy a Mjolnir config template to a new directory, named whatever you wish. Then, in the metadata.toml in that directory, change the name field to be unique to your system and update the other metadata fields accordingly. Register your system with Brokkr and set it as the default, just like we did before, but with the default switch. And finally, check that Brokkr is actually using the new system by looking at the output of Brokkr-h version or Brokkr configure system. As the main config file is where you'll be spending much of your time with Mjolnir, it's worth a closer look. The general section has options that affect Brokkr's overall operation, such as the default output path. The auto-SSH section has settings for the reverse SSH tunnel. The step section specifies custom parameters for the pipeline steps referenced in pipelines. And the pipeline section defines the properties and steps of the pipelines to execute. In more detail, we can see here various properties in the general section, including the ones we mentioned, as well as the auto-SSH section. It allows you to establish a tunnel to a proxy server that you control to allow you to access your sensors even if you have no direct IP or internet to them. However, if you're not interested in that, you can simply comment out this section. Looking closely at the pipeline section, we can see the properties of the pipeline, and we can see the input, process, and output steps specified for that pipeline. These steps can either be referenced directly as presets, as we can see for this ping preset, or they can be referenced as names in the steps table, which allows you to specify custom parameters, as we'll see in a moment. The main config file can contain custom data types, which get merged with those in the relevant preset for each step, as we can see here. And they get automatically inserted into the data types field of each step if the names match. We see here we have several steps. We have 2 input steps with some custom settings. And we have 2 output steps, one which defines custom data types, and the other one which is the same as our default ping input preset, but allows us to specify other settings. You can have as many steps as you want that map to one preset, but it makes sense to specify different settings for each one, as we see here. Now, let's take a look at a device preset file, as we can see here. It has parameters for the whole device preset, metadata, which follows the format in metadata.toml, type presets, which allow sharing of common attributes between data types, data types, which define the key properties and metadata for each value read in by the sensor in question, and finally, input, process, and output presets associated with that device. Here's an example of a fairly minimal device preset for the BME280 pressure, temperature, and humidity sensor. We can see the name of the preset, which is what actually gets looked up, not the file name. We can see the data types for the preset, which specify each type of value that the sensor reads. These get inserted into the data types key, assuming the keys match, in the actual input preset itself. We can see the input preset here for the BME280 via I2C, because it can also work via SPI. We see the module path for the module to load that contains the actual step class, as well as the class name, and the dependencies it needs. These will get installed automatically if you type Brokkr install dependencies. It will install the dependencies for all of the steps used in the current system. Finally, we can see some individual step-specific settings which get fed to the init method of the particular step. Here's an example of a minimal output preset. It looks very similar to the previous input preset, except it's missing data types because it doesn't need to create new data values, and it has different custom parameters that get fed to that individual type of step. Plugins from Mjolnir can be loaded from Python files in the plugins directory of your system config package, or from an already installed Python module. They will always have as a superclass a subclass of pipeline step, and their init method can take arbitrary arguments as specified either in the preset or in the steps table. You just need to make sure to pass keyword arguments to super.init. Finally, the main logic is typically all contained in one abstract method that the superclass has, and it needs to be overridden by the plugin class to do something useful. Let's take a look at a transform plugin, which takes some input and converts it to some output. We can see that it inherits the base pipeline step API, which has a method execute, which takes some input data and converts it to some output data. If we look at the preset, we can see it looks fairly familiar to those for built-in Brokkr pipeline steps. However, instead of a fully qualified Python module path, it just has the name of the file in the plugins directory. Class name looks familiar, and the is plugin key is set to true, so Brokkr knows to load the plugin. It only has one parameter, name, which is fed to the superclass of the plugin. And we can see several sections in the plugin which should be replaced with your own code to do whatever you want your plugin to do. Now, let's look at an example of an output plugin. We can see here that it implements the file output step API, which again has one abstract method, writeFile, which takes some input data and an output file path and writes the file, returning none. Again, we can see some parameters in the preset. In this case, again, we have name, which gets fed to the superclass, but we also have extension, which gets used by our class. Again, we can see the sections in the code of the example plugin that would be replaced with your own functional logic. Value input steps are useful for working with sensors and other devices. They take care of most of the hard work of decoding and converting data. All you have to do is read it in a raw form. They have one method, readRawData, which takes an input data argument, which is typically none, and outputs the raw data as a list of whatever the raw data type is. We can see here we have our usual data types table in our preset, which lists the various data attributes that should be read. They get inserted into the data types key of the particular plugin, and all of those attributes then get sent to the init method for your code to handle. Again, if we look at the plugin, we can see several sections that should be replaced by your own functional logic to do whatever you want it to do. The AttributeInput plugin type is easiest to use of all. All it needs is a sensor object, whether written by you or by a third party, that has properties or methods to read its data. All you have to do is configure your data types lookup table in the preset, which then gets fed again the data types key of your input preset. And then those properties then get fed into the init method of your sensor class, which then reads the data. You would want to replace these elements with the functional logic specific to your sensor. Let's review the current status of the project so far. We've had 3 alphas, 3 feature releases, and 13 point releases, and Brokkr and Sindri have both been in use for over 6 months on HAMA 2 sensors. And uptime for the whole system has increased from over 95% to now over 99%, and test deployments are currently underway with eMesh and other experimental sensors. Taking a look at the roadmap, in Brokkr 0.4.0, we expect to have new system monitoring features, IPCQs for communication between pipelines, more sensors and protocols, and asynchronous data stream support. In Brokkr 0.5.0, we'll have full support for more types of uplinks, automated setup, deployment, and checkout, and a watchdog service to restart Brokkr in case things go wrong. In Brokkr 1.0, we'll introduce full unit and CI tests, docs and doc strings, number of guides to help make it easier for you to write plugins, split several modular components into separate packages, and polish Brokkr for release. Finally, in 1.1.0, we expect to have full remote config and command uplink capability, config validation, and more core pipeline steps. Meanwhile, for Sindri, the server, Sindri 0.3.0 should have full support for the new telemetry and trigger data planned to be featured in later Brokkr versions, as well as many minor UI and UX improvements. Sindri 0.4.0 will add the remote uplink of sensor data, add the master all unit dashboard, and add multi-unit support. Sindri 0.5.0 will be ported to the common Mjolnir multiprocess pipeline log and configuration architecture currently used by Brokkr, and add a higher level API for easier use. Sindri 1.0.0, like Brokkr 1.0, will have unit and CI tests, docs and doc strings, and be polished for release. And finally, Sindri 1.1.0 will have the remote settings and command support, also featured in that same Brokkr version. We have a number of other projects currently planned or in work beyond just the improvements to the core Brokkr and Sindri packages. Our presets, plugin, and system configuration packages are being converted to cookie cutter templates, so you can very easily get started with them without a lot of boilerplate or extra work. We're also building a GUI for easily creating a preset, plugin, or system configuration package without you having to do much more work, and also checking and validating that you've done it correctly. We also are adding plugin integration with the Spider IDE, and we're working a number of plugins, including a Slack bot, alerts, processing, and more. Finally, we're currently developing a comprehensive guide and docs to make it as seamless as possible for you to create your own Brokkr presets, plugins, and system configuration packages. However, the long-term vision of Mjolnir is not to create a framework or lots of Python packages. We want to build a community with a whole ecosystem of contributors, plugins, presets, and more, collectively benefiting the cost of low-cost, high-impact, accessible open science for everyone. But to do that, we need you. Whether you're a student, researcher, programmer, or anything in between, we've got something for everyone. Do you use Brokkr, Sindri, or Mjolnir in your work? Please cite us and drop us a line. Let us know what cool things you use us for. Find a bug? You want a feature? Open an issue on our GitHub. You want to add a new device? It's pretty easy. Just make your own preset. And if you want, contribute it to the Mjolnir presets repository so everyone can benefit. You want to support a new protocol in Brokkr and Sindri? Create a plugin. You can also contribute those to our repositories as well. Finally, if you want new core functionality that can't be provided with our existing framework, help contribute on GitHub. We'd love to see you there. Well, folks, that's all we have for now. But if you have any questions, feedback, suggestions, or anything else, please ask during the Q&A or get in touch. We'd love to hear from you.